Hello everyone, my name is Amit Meghnani and today I'm going to present my paper named Deriving Translational Acoustic Subword Embeddings. So let's start with the introduction. Acoustic word embeddings are defined as a fixed dimensional vector representation of spoken words, and in similar fashion, acoustic subword embeddings are defined as the fixed dimensional vectors of spoken subwords. Now, in this work, we try to obtain the acoustic subword embeddings by decomposing the acoustic word embeddings into subword embeddings in such a way that the we can get back to the original acoustic word embedding by translating the acoustic subword embeddings. For example, if we have a word aiming and if we have obtained the acoustic subword embeddings of aiming, which is A, IM and ING, we can translate them in the embedding space like this and we can get back to the original acoustic word embedding. And when we say translation embedding space, basically we say they are getting translated by subword embeddings. So we have null, then we translate. So we add A, then we get to the unit embedding of unit A, then we translate A with the subword embedding IM, then we get the aim, and then we again translate with the subword embedding, and we get the aiming. Now again, one more point to highlight, and I would like to emphasize here is that the order of the translation, the subword embedding matters. If we translate from A to ING, then the final outcome will sound different. So that's the point, that order of the subword embedding matters. And while designing, while decomposing them, we'll put that thing in our mind. So let's start with the data preparation part, and we use LibreSpeech dataset and we force align them to get the spoken one boundaries, and then we train a byte pair encoding tokenizer on the text available from the LibreSpeech recordings, and with a vocabulary size of 200, and then we define our dataset as a collection of words which has exactly 3 BP tokens and duration greater than equal to 0.5 seconds, which is a standard choice in the literature. And this, since this study is the first of its first kind, which is looking at the acoustic subword embeddings, so we started with the some constraint, which is that we only are looking at the moment only the words which has 3 BP tokens or 3 subwords. And then later in the future, we'll try to expand this, but at the moment it is only 3 subwords. So let's start with the acoustic word embedding extraction. So we use a quite stabilized network setup in this domain, which is already quite good, which can be used to obtain quite good acoustic word embeddings, which is known as the correspondence autoencoder. And in that, in autoencoder, in basically encoder and decoder here are GRU units, so recurrent neural network. So it is called as a CAE-RNN model. In that we have an input sequence of a word, and then our target output is the same word but a different spoken instance. By doing that, we make sure that while learning the embedding representation, this is invariant to any mismatch in the duration or speaker identity by feeding the input output pair as a different instance of the same spoken word. So more detail you can read about the baseline papers or our paper. And then once we have got the acoustic word embedding A, we will try to decompose into acoustic subword embeddings. And remember, since we have only 3 subwords, we have 3 fit for all neural networks, and we can get and they are position dependent, so the weights are not shared among them, so they are position dependent fit for all neural network. So we get the embeddings E1, E2, E3 for 3 different position of a word. So we derive that and we train this setup with the joint classification task, and we take the embeddings finally from the last layer as our acoustic subword embeddings. And since we want to get the embeddings in a way that we should be able to reconstruct back the original embedding, so we add another term called similarity loss here, which is the cosine distance between the reconstructed embedding and the original embedding. Now the reconstruction, we want it to be translational, so we reconstruct with these equations. Here F projection is like a linear projection layer if you're using it, otherwise it is just a simple translation of the acoustic subword embeddings. So we put this criterion so that the translation property holds and we can reconstruct back the original embedding. Now, to evaluate acoustic subword embedding, we propose a three adapter version of average precision metric, which is used for word discrimination task of acoustic word embeddings. So the first one is APHD, which is the average precision for the subword discrimination task. And again, here there are three positions of a subword. Like in a word, we have three words. It could be at the start, middle, or at the end. So we have this metric for three different position. Then another metric is APRW, which is average precision for the reconstructed word. So it is between the original spoken word and the reconstructed word, which are reconstructed by this either this or this equation. And there is another thing we tried. Since we can get the acoustic subword embeddings, we can generate acoustic word embedding of a written word, which we haven't seen before, or even if we have seen, but we can construct it from a written text modality. So we call this metric APCW, which says average precision of the acoustic word definition task between the original and the constructed acoustic word embedding of a written word. So again, we will discuss about the written word construction in following section, but those three metrics are defined, and then let's talk about the results and discussion. So our first aim was to get a high quality acoustic word embeddings, and we explore two input features. One is Hubert and the second is MFCC input, and we can see that self-supervised learning based features like Hubert outperform MFCC with a lot of margin, and we have got like very high quality acoustic word embeddings, which is good as we have to decompose them to subword embeddings. And then you can see here the result for the acoustic subword embeddings, and you can see with the different uh, all possible combination of decomposition model with different laws and features, and whether we have used projection layers or not, and APHD metric for three different position, and then APRW and APCW, which is for reconstructed word and constructed word. So the takeaway from this tables is high quality acoustic word embeddings from Hubert with AP of 0.97 on the test set is obtained, which is like a highly discriminative acoustic word embedding. And then we got the highly discriminative acoustic subword embedding without using any time boundaries. So that's also one important point we want to highlight, that we haven't used any time boundaries of the subwords. We directly derive them from the embedding space and don't use any time boundaries for spoken subwords. And then high quality reconstruction of acoustic word embedding from the subword embedding is possible, which is measured by APRW and in some way from APCW, because it is the discrimination task between the reconstructed word and the original embedding, and this is the reconstruction of acoustic word embedding from the written form. So you can see that these are the highlights from the table. And then let's jump into the qualitative analysis of constructed acoustic word embeddings. So for this, we did a small experiment named Word2 acoustic word embedding, where we generated an acoustic word embedding of four random written words from the test set, which are unchained during the training. And they are constructed with the Hubert-based acoustic subword embedding. And then we compute the top three nearest neighbor from the test set, which are derived here, which are described here. And then you can see the quality of the nearest neighbor obtained. So in the case of best model setup, we have for every word in the test set, which we reconstructed from the text modality by first getting the BP token, and then since so once you have the BP token, and for more detail you can refer the paper. And what we did is we created dictionary for every subword from the training set, and for every subword we have pulled all the instruction of that subword from the training set to get a one fixed embedding for each subwords. So more details are available in the paper. So now we have representation of each subword which we derived from the training set, and then we can use them to reconstruct words from the test set. So we have already have embedding for this thing, and we just simply add them and we can get the embedding of the final word. And you can see that the nearest neighbor is actually same as what we constructed from the written form. In this case also, in this case, or if they are not same, they are kind of spoken in spoken terms, they are quite similar. But when we do the same experiment with the APCW, which is this one, first line, and it doesn't, and there was no reconstruction loss, hence the derived subword are just random and doesn't match with the original written embedding that we generated. So it is just a random vector. And when we actually, as you mentioned, we swap the subwords here in the introduction, the word changes. So we try to do experiment here where we try to took a best model and swap the subword position while getting the final model. And we saw that the caustic word embedding of the when we swap the subword position, it changes the nearest neighbor, and you can see only kind of first word matches, but the rest two doesn't match, and so the reconstructed word is the nearest neighbor doesn't match with the original words. So this shows that the order of the subword matters. And then to make this our point, so we can see that the order, the swapping the subword does change the how the word sounds, and which is reflecting in this table. And then we have a TSNA plot of the acoustic word embeddings from the test set, and you can see that they are quite well separable, in the clusters, in well separated clusters. And these are derived from the best model of a Hubert-based CERNN, which has the average precision of 0.97. And then we have the acoustic word subword embedding plot, which are like five most frequent subwords from the test set derived from the best decomposition model, which is APCW equal to 0.72. And you can see that even the subword embeddings are quite well separable. And in the cluster, you can see every subword in a different cluster, and that they are well separable. So conclusion and future work. So let's describe. So we have a test showed we have obtained high quality acoustic subword embedding by decomposed acoustic word embeddings. And then acoustic word embeddings can be reconstructed by translating acoustic subword embeddings in the embedding space. And then we also show that acoustic word embedding of a written note can also be constructed by acoustic subword embeddings. So that's like converting a text modality into a acoustic word embedding speech modality in embedding space. Now, future research direction of this would include combining the acoustic word embedding subword embedding extraction module into a single framework for variable number of subwords, as we have the different module for both embeddings. And we are, as a pilot study, we started with the only three subwords, so we'll be moving on with variable number of subwords and then see what are the different approaches to achieve the same. Thank you.